This video covers section 5.2 review for trigonometry, part 2, finding the roots of complex numbers and using de Moivre's theorem. So we've seen before that when you have a power on a complex number in polar form, you multiply that power times the angle. And you take the modulus or the length of the complex number to that power. And the other thing that we have to always remember is that when you take, or when you're finding complex square roots, there's always two. There are two complex square roots of any number. And when you find cube roots, there are 3 cube roots. And so on. If you have to find the 5th roots of a number, there's always 5 of those. So we have to be a little extra careful when our powers on our complex numbers are fractions. So what we have to remember is that 50 degrees is virtually the same as 50 plus 360 degrees. So we're going to replace that 50 degrees with 50 plus 360k. And now remember, we're taking this to the 1/2 power. So we have 49 to the 1/2. And then we have cosine of. We take 50 times 1/2, which is 50 over 2, and 360 over 2. 50 over 1/2, which is 25, and 360 over 2, which is 180. And this allows us to find the two of them by setting k equal to 0 and 1. And so from this, I can draw you a little picture. The first square root is going to be at 25 degrees. And the second square root is going to be at 25 plus 180, which is over here. Those are going to be our 2 square roots. They're going to have length 7, because 49 to the 1/2 is 7. 25 plus 180k. And so when finding square roots, you're going to let k equal to 0 and k equal to 1, because there's our 2 of them. So we're going to leave this in polar form because we don't know what the cosine of 25 is without a calculator. Cosine 25 plus I sine 25. And the next one's going to be 180 past that. 180 plus 25 is 205. So with this technique here, we can find any root. We can find all complex roots of any complex number. The cube roots of this number. So remember, we're looking at 165. That's the number. But when we want cube roots, we divide that by 3. And that gives us 55 degrees. So that means the first cube root of that number is at 55 degrees. But remember, 165 degrees is the same thing as 306 plus 360k. Divide that by 3. That means we're adding 120 degrees with that. So we've split the circle up into 3 equal pieces: 55, 55 plus 120, and then 55 plus 120 plus another 120. And we just have this thing split up into equal segments where each of those are 120 degrees apart. If you do fourth roots, then you split into 4 equal pieces, then they're separated by 90s. So that's a picture of what these cube roots look like. And then we'll just find them in polar form. So we got 55. We got 55 plus 120. 175, and then 175 plus 120. 295. So you could do that math off to the right-hand side and just write them in there like that. But I'm going to go through the full analysis again here. We got 125 times cosine of 165 plus 360k plus I sine of 165 plus 360k, and we're raising that to the 1/3. So we go out and take 125 to the 1/3, which we know is going to be 5. And then we take 165 over 3 and 360 over 3. All right, so 165 over 3, as we said a little bit ago, was 55 degrees. And then we add multiples of 120 to that. Okay, so we're going to leave this in polar form. Now we run through the k's. K equals 0, k equal 1, k equal 2. So like I said a little bit ago, you could just literally take these numbers and go straight into what I'm going to do now. 5 cosine 55 degrees plus I sine 55 degrees. That's the first one. Second one, 5 cosine 55 plus 120 is 175 plus I sine of 175. Last one, when k equals 2, cosine of 295 plus I sine of 295. Now, if you go k equals 3, you're going to be back up at the k equals 0, and then you'll just be back around in the circle, and so that's why we stop. 3 cube roots go from 0 to 2. All right, in the next example, we're going to find all the complex roots, but we're not going to leave it in polar form. We're going to go ahead and write it in rectangular form. All right, so the process is still the same. We need to start with 2 pi over 3. And add 2k pi to it. Or 2 pi k, doesn't matter. And we're taking this to the 1/4 power. So we're going to get 16 to the 1/4, which is the 4th root of 16, or 2. And then we have to divide all this stuff by 4. So 2 pi over 3 divided by 4 is 2 pi over 3 times 1/4, or pi over 6. Now, 4th roots, we're taking the full 360 divided by 4, which is 90. So I'm going to start drawing my picture now, because I know the first one's pi over 6, which is 30 degrees. And then by taking 2k pi and dividing by 4, this is when we get the plus pi over 2k. So that means these are all going to be in 90-degree increments. Okay, so we've got the first one at pi over 6. The second one is going to be pi over 6 plus pi over 2. Two pi over 3. The next one is going to be 2 pi over 3 plus pi over 2. Which is 7 pi over 6. And the last one's going to be 7 pi over 6 plus another pi over 2. We should recognize that as 5 pi over 3. All right, so we've got 2 times these numbers. So a lot of times we call these, when k equals 0, we call this z sub 0. When k equals 1, that's z sub 1. These are all of the fourth roots of that number. All right, so I like to do this work over on the other side, the adding to get my angles. So I have z sub 0 is going to be 2 cosine pi over 6 plus I sine pi over 6. Cosine 2 pi over 3 plus I sine 2 pi over 3. Cosine 7 pi over 6 plus I sine 7 pi over 6. 2 times cosine 5 pi over 3 plus I sine 5 pi over 3. So those are all the fourth roots of that complex number. And now we write them in rectangular form. Cosine of 30 is root 3 over 2 plus I times 1/2. That's going to give us root 3 plus I. Cosine 2 pi over 3, that's cosine of 60 in quadrant 2, so that's negative 1/2. And then sine of 60 in quadrant 2 is a positive, root 3 over 2. So we get negative 1 plus root 3I. And then cosine of 30 degrees in quadrant 3 is negative rad 3 over 2. Sine of 30 degrees in quadrant 3 is minus 1/2. So we get negative root 3 minus I. And then the last one, cosine of 60 in quadrant 4 is 1/2. And the sine of 60 in quadrant 4 is negative root 3 over 2, which is 1 minus root 3I. And there are all the fourth roots of that complex number. The complex cube roots of 8I. We know that 8I has a modulus of 8 and an angle of pi over 2. But remember, we have to always add and get all coterminal angles in there. And so if I'm going to take the cube root of that, I'm over here thinking, okay, 90 divided by 3 is 30. there's going to be my first one, z sub 0. And now we're taking 360 divided by 3. And so that's 150. And then 150 plus 120 is 270. So let's make that picture look a little bit better so we have symmetry. So 30 plus 120 is 150. 150 plus 120 is 270. And 270 plus 50 plus 120 is 270. And 270 plus 120 is 390. So something seems a little bit weird here. And then the 270 plus the 120 is 390, which is the 30. Okay, so we got them all pinned down, 30, 150, and 270. So we're going to take 8 to the 1/3, which is 2. We're going to have cosine of 90 over 3, which is 30, plus 360 over 3, which is 120. All right, so z sub 0 is 2 times cosine 30 plus I sine 30. C1 is 2 times cosine 150 plus I sine of 150. The third complex cube root of 8i is cosine 270 plus I sine of 270. All right, so now putting these in rectangular form, cosine of 30 is root 3 over 2, and sine of 30 is 1/2. That's root 3 plus I. Cosine 150, well, you see that's just a reflection over the y-axis, so that one's going to be negative root 3 over 2 plus 1/2 I, so it's going to be negative root 3 plus I. And then for the 270, cosine of 270 is 0, and sine of 270 is negative 1. So this gives us negative 2i. And so those are all the complex cube roots of 8i. Now, the last one's the complex cube roots of negative 1. So remember, what we're doing here is we're solving, by finding the complex cube roots of negative 1, we're solving the equation x cubed equals negative 1. You learned how to do this in algebra. However, I think doing it with Demois's theorem is so much slicker. It's kind of cool. All right, so remember what negative 1 is. Negative 1 sits on the left side on the x-axis, so it's an angle of 180 degrees. Its modulus is 1. Its length is 1. So we've got the cosine of 180 degrees plus 360k plus I sine of 180 degrees plus 360k. And if we want to take the cube roots of that, x would be negative 1 to the 1/3. Most people will just say that negative 1 to the 1/3 is negative 1, but there's 3 solutions to that. The other 2 are complex. So we have to take this whole thing to the 1/3 power. So let's start drawing our little picture here. So we had 180 degrees. We're going to come along and we're going to divide it by 3. which is 60. So there's the first one, z sub 0. But 360 divided by 3 is 120. So we've seen this before. The cube roots are all split by 120. Okay, length of 1. So the first one's going to be 60 degrees. When k equals 0, cosine of 60 plus I sine of 60. And the second one's 60 plus 120, which is 180. So z1 is cosine of 180 plus I sine of 180. And then 180 plus 120 is 300 degrees. And now we've got everything split by 120. So I like to compare the two pictures with each other. They look very much the same, just rotated. So the last one we said was 180 plus 120, which is 300 degrees. And that's the third cube root of -1. Okay, now putting them in rectangular form, we got cosine of 60 is 1/2 plus sine of 60 is √3/2. Cosine of 180 is -1 and sine of 180 is 0. And 300 degrees, well, that's just the reflection about the x-axis from the first one, so it should just be 1/2 minus √3/2i. And those are all the cube roots of -1. So another interesting problem would be all the complex cube roots of 1 instead of -1. The cube roots of 1 are the picture rotated this way. And so they're pretty much the same numbers, just with different signs. All right, so this concludes the video for section 5.2, part 2, the roots and de Moivre's theorem with complex numbers.